Thanks for joining me in today's lesson. In this first tutorial, we will be able to recognize sequences and write a rule to describe them. So we're in our brand new chapter in section 11.1, and we're looking at sequences and sigma notation today. So a sequence is simply a pattern of numbers separated by a comma, and each term in our sequence has a specific name. For example, a sub 1 represents the first term, and a sub 2 is the second term, and so on and so forth. A sub n represents the last of n terms. So n is always going to be the number of terms that you have. Sometimes a sub 1 won't have the little subscript of 1, it'll just say a, so that it's implied that it's a 1, but every other term will have its corresponding subscript. So example number 1, we're finding the first 4 terms of each sequence. Oftentimes we are given a rule, and that rule is a sub n equals some sort of expression. And when we're given a rule, it's pretty easy to find whatever term you want. Basically, you just plug in the number of the term into your rule to figure out what that term will be. For example, if we're looking for the first term, we would simply plug in a 1. If we're looking for the 6th term, we'd plug in a 6. If we're looking for the 100th term, we'd plug in 100. So that's what's powerful about having this rule. So I'm going to put a little colon here. If I'm looking for the first 4 terms, I'm going to plug in a 1 and a 2 and a 3 and a 4. If I plug in a 1, I get 3 times 1 minus 2, which is 1. I'll separate my terms with a comma. If I plug in a 2, I get 3 times 2 minus 2, which is 4. When I plug in a 3, I get 3 times 3 minus 2, which is 7. And I plug in a 4 to find my 4th term. 3 times 4 is 12, minus 2 is 10. And you can actually see that the pattern in these terms, you're adding 3. And if you remember from a previous class, this is describing an arithmetic pattern. Now we're going to focus in a later tutorial specifically with arithmetic patterns, but just to remind you, when you're adding the same number to get from term to term, that's an arithmetic pattern. And what we're adding is a 3, and it's no coincidence that the coefficient in my rule is a 3. Whatever this coefficient is in an arithmetic pattern, that's how much you're going to be adding to get from term to term. So those are the first 4 terms of this sequence. The next sequence, we have a new rule. A sub n equals this. So we've got something going on in the numerator, and we've got something going on in the denominator. I'm going to put my colon, and let's list the first 4 terms. Same thing, we're going to plug in a 1, 2, 3, and 4. So when I plug in a 1, I get negative 1 raised to the first power, which would still be just negative 1. And in the denominator, I get 2 times 1 minus 1, which would be 1. So that's basically negative 1. I could maybe reduce that, but sometimes it's helpful to keep it in unsimplified form, if you will, to see the pattern. But that is ultimately a negative 1. Let's plug in a 2. This time we're going to be squaring the negative 1, and that, of course, will create a positive 1. And in the denominator, 2 times 2 minus 1 would be 3. Next, I'm going to plug in a 3, so that now I'm cubing my negative 1. Raising a negative to an odd power would keep it negative. And in the denominator, 2 times 3 minus 1, of course, is 5. And lastly, I'll plug in a 4 to find my 4th term. Now I'm raising to an even power, so it's going to stay, or it's going to go back to positive. And 2 times 4 minus 1 is 7. So these are the first 4 terms here. This is not an arithmetic pattern. Now you might see in the denominator that there's an arithmetic pattern to get from 1 to 3 to 5 to 7. So you're adding a 2, which is, again, why the coefficient in the denominator is a 2. But in the numerator, you're bouncing from negative 1 to positive 1 to negative 1 to positive 1. And that's actually a geometric pattern, and that's why we have an exponent up here. We'll explore all these things in later tutorials specifically, but for right now, I want you to be able to find specific terms by plugging in those values. My last one is actually a piecewise sequence. We actually have 2 different pieces to plug into. The top piece if n is an even number, and the bottom piece if n is an odd number. So if we're looking for the first 4 terms, again, we're plugging in a 1, 2, 3, and 4. Since 1 is odd, I will be plugging the 1 into this bottom piece, and 1 divided by 1 is 1. Since 2 is even, I'm going to plug a 2 into the top piece. 3 times 2, of course, is 6. 3 to find the 3rd term. 3 is back to being odd, so I'm going to plug it into the bottom piece and get 1/3. and 4 is even, of course, so 3 times 4 is what I'd get to get my fourth term. Now this, if you just see these terms and try to go backwards, which is what we're going to do on the next slide, it might be a little bit more difficult. Perhaps you want to continue this pattern. The next one would be 1/5, and then I'm plugging in a 6, which would give me 18, and then a 1/7. Perhaps the more terms we have, the easier it is to see the pattern. And now you can maybe see that every odd term is a fraction ultimately, and every even term is a multiple of 6. So it might be a little bit easier for you to be able to write the rule. But that's just plugging in and finding the first 4 terms. Let's go ahead and write rules now. That's what example 2 says. We're writing an expression for the nth term of each. That's basically writing the rule. So here's our first one in part A. We've got 1, 3, 5, 7. I know that you can continue this pattern, and that's important to be able to understand how to do the pattern, but let's see if we can write the rule. A sub n is going to equal some sort of expression. Well, we already sort of gave away a hint for this one. In fact, these are the denominators in part B, I believe, in example 1. So this is following an arithmetic pattern since we're adding the same number, in this case a 2, to get from term to term to term. It's arithmetic. And what we're adding becomes a coefficient. So I know that 2 times n has to be part of my rule. Now what I like to do is plug in a 1 and see if I get my first term. So if I plug in a 1, I get 2 times 1, which is 2, and unfortunately that is not what my first term is. So this is where I need to do some sort of adjustment. I'll subtract 1. So 2 times 1 minus 1 would work. Let's check the next couple terms. If I plug in a 2, I'd get 2 times 2 minus 1, and that's 3. If I plug in a 4, I should get my fourth term. 2 times 4 minus 1 is 7, and it looks like this is going to be our rule. Let's look at part B. This time we've got 2 to 5 to 10 to 17 to 26. This is not arithmetic because we're not adding the same number. We're adding a 3, then we're adding a 5, which obviously is not the same, then a 7, and then a 9. So it's almost like there is a pattern in what we're adding. And the 3, 5, 7, and 9 that we're adding, yes, that is an arithmetic pattern, but that is not an arithmetic pattern with the terms that we're talking about, 2, 5, 10, 17, 26. This pattern, though, is easily recognizable. When you start adding consecutive odd numbers, that's a dead giveaway for what this pattern is. These numbers, though these numbers are actually not the numbers that you have memorized, these are all exactly 1 away from a set of numbers that you do use all the time, the perfect squares. When you add consecutive odd numbers in a pattern, you are talking about a perfect square pattern. So a sub n, of course we're writing our rule, I know that there's going to be something with n squared. Now, obviously, if I plug in a 1, 1 squared is not what my first term is. So this is where my adjustment comes in. In this case, I'll just add 1. And then I'll check the rest of them. 2 squared plus 1 would be 5. And 3 squared plus 1. And 4 squared plus 1. And 5 squared plus 1. These are all 1 higher than our perfect squares. And again, the reason why I will always know there's a perfect square pattern is because you will be adding consecutive odd numbers. And a neat little illustration of that is a nice visual here. Let's start with the first perfect square, which is simply 1. And it's actually just literally a perfect square, 1 square. If I want to get to the next perfect square, of course, 1 would go up to 4. I would have to add 3 more squares to make that next perfect square. 1, 2, 3 more squares. And if I wanted to get to the next perfect square after 4, which of course is 9, I would have to add 5 more squares. 1, 2, 3, 4, 5 to get to the next perfect square. And the next perfect square after 9 would be 16. Guess how many squares I'd have to add to get from 9 to 16? 1, 2, 3, 4, 5, 6, 7. And each of these is the next biggest square. We're adding consecutive odd numbers, 3 and then 5 and then 7 to get each of our perfect squares. I think that's kind of a neat illustration of our perfect squares pattern. So here's our final example, at least in writing our expressions for today. 1, 1, 2, 3, 5, 8, 13, 21. I'd like you to pause the video right now and look at this sequence of numbers and see if you can figure out the pattern and see if you can tell me what comes after the 21. Pause now. If you have not yet figured out this pattern, let me give you a hint. Each term depends on the previous two terms. Look at that, pause again, and see if you can figure it out now. So thanks for trying that, and I hope that you had success. Each term in this sequence is found by adding the previous two terms. So this 5 comes from the 2 plus the 3, and this 13 comes from the 5 plus the 8. So my next term must be 13 plus 21, which is 34. And my next term would be 21 plus 34, which would be 55, and so on and so forth. This is actually called the Fibonacci sequence. You might have seen this before, the Fibonacci sequence. It's a pretty popular sequence. Let's see if we can write a rule for this. Now, to be able to write this rule, we have to define this recursively. I'm going to say defined recursively. What that means is we cannot just write a single rule that works. Defining something recursively means we actually have to define the first couple terms first. So for example, I need to say that a sub 1 is going to be the number 1. And that a sub 2 is going to also be the number 1. Since every term, at least starting with the third term, depends on adding the previous two terms together, I need to define what what the first two terms actually are. And then I can write my rule. So this is what I mean by defining something recursively. It depends on what we start with. So a sub n, any term, at least starting with the third term, is the previous two terms added up. So if a sub n is the term that I'm looking for, the term previous to a sub n would be a sub n minus 1. And the term previous to that one would be a sub n minus 2. And if I add those two previous terms together, I would have a sub n. And that's how you can define the Fibonacci sequence. Again, we have to define it recursively by actually telling people what the first two terms are going to be, and then every term after the second term will be the previous two terms added up. Now, what's difficult to do with something that's defined recursively is find, for example, the 100th term. If you wanted to find a sub 100, you would need to know what a sub 99 and a sub 98 are equal to, so that you could add them together. So to find a sub 100, we actually have to find all 99 of the first terms. So we would have to continue this pattern many, many times. It's not as easy as something like in part A. If I wanted to find the 100th term here, I just plug in a 100 and I get 200 minus 1, 199. Pretty simple. Same thing over here, 100 squared plus 1. But to find the 100th term here is a little bit more difficult. So that's writing our rules and using our notations here. Thanks for watching this tutorial. I'll see you in the next one.